Welcome to this problem walkthrough. Today, we're tackling problem number 524, longest word in dictionary through deleting. In this problem, we'll explore how to identify the longest word in a dictionary that can be formed by deleting some characters from a given string. Let's dive in and break it down step by step. In this problem, we are given a string S and a list of words called dictionary. The goal is to identify the longest word in the dictionary that can be formed by sequentially deleting some characters from the string S. Importantly, the characters in S must remain in their original order, even after deletion. If multiple words have the same length, we prioritize the lexicographically smallest one. For example, if two words like ABC and ABD are valid, we would return ABC because it comes first alphabetically. If no word can be formed at all, we simply return an empty string. Let's also keep in mind the constraints. S can be up to 10,000 characters long, while the dictionary can contain up to 1,000 words, each up to 10,000 characters in length. This means the solution must handle large inputs efficiently. To make this more concrete, let's look at the first example. Here, the string S is app plea, and the dictionary contains the words ale, apple, monkey, and plea. By deleting specific characters from S, we can form several words from the dictionary. For instance, ale can be formed by removing characters like B, P, and C. Similarly, apple and plea can be formed through their respective character deletions. Among all these, apple stands out because it is the longest word that can be formed. Therefore, the output for this example is apple. In the second example, we again have S as app plea, but this time the dictionary contains only the single letter words of B and C. By deleting characters from S, each of these words can be formed. Since they all have the same length of 1, we select the lexicographically smallest word, which is a. So the output in this case is simply a. Another example is when the string S is XYZ and the dictionary still contains a B and C. In this case, none of the words in the dictionary can be formed by deleting characters in S because the characters in S don't match any in the dictionary. This brings us to the output for the third example, which is an empty string. Since no word from the dictionary can be formed by deleting characters from S, the result is just an empty string, represented as. This highlights one of the edge cases to consider. When there is no match at all, the algorithm should return an empty string. Now, let's summarize the constraints and edge cases to ensure that the solution works for all scenarios. There are a few important considerations to keep in mind for this problem. First, if the dictionary is completely empty, the output should also be since there are no words to form. Second, if no matches exist between the dictionary and the string S, we must still return. Third, when there are multiple valid candidates of the same length, the solution should return the lexicographically smallest word among them. Fourth, some words in the dictionary may require all characters from S to form, while others may only require a subset. It's essential to ensure correctness in both scenarios. Finally, given the constraints, the algorithm must handle large inputs efficiently, especially since S and dictionary can both contain up to 10,000 characters. Balancing correctness with performance is key to solving this problem effectively. To solve this problem, we first consider the brute force approach. The idea here is to generate all possible subsequences of the string S and then check which of these subsequences are present in the provided dictionary. Once we have all valid subsequences, we return the longest one. In the case of ties, where multiple strings have the same length, we choose the lexicographically smallest string. The steps are straightforward. First, generate the subsequences of S, which involves exponential time complexity since there are 2 raised to the power of the length of S subsequences. Next, we check each of these subsequences against the dictionary to filter out valid ones. Finally, we pick the longest valid string, resolving any ties lexicographically. However, this method is computationally expensive. With a time complexity of 2 to the power of n asterisk m, where n is the length of S and m is the size of the dictionary, it quickly becomes infeasible for large strings. Additionally, the space complexity is also exponential due to storing all subsequences. While simple in concept, the brute force approach is impractical for real-world use cases with large inputs due to its inefficiency. To address the inefficiency of the brute force approach, we can use an optimized two-pointer technique. This method takes advantage of the fact that we only need to determine whether a word in the dictionary can be formed as a subsequence of s. Using 2 pointers, one for the string s and one for the current word from the dictionary, we can efficiently check if all characters of the word appear in sequence within s. As we iterate through each word in the dictionary, we move the pointer 4s forward whenever there is a character match. If we successfully match all characters of the word in sequence, it is deemed a valid subsequence. Throughout this process, we keep track of the longest valid word, choosing the lexicographically smallest one in case of ties. This approach is far more efficient, with a time complexity of n*m, where n is the length of s and m is the total number of characters across all dictionary words. Additionally, the space complexity is constant, as no extra data structures are required. This makes the two-pointer approach a significant improvement in terms of computational efficiency and scalability. The two-pointer approach is not only efficient but also simple to implement, making it a strong candidate for solving this problem. However, we can further optimize the process by first sorting the dictionary. Sorting the dictionary allows us to prioritize longer words and resolve ties lexicographically upfront, simplifying our result selection process. To achieve this, we sort the dictionary by 2 criteria: first, in descending order by word length, and second, in lexicographical order for words of the same length. Once sorted, we can iterate through the dictionary and use the two-pointer technique to check if each word is a subsequence of s. The benefit of sorting is that the first valid word we encounter will automatically be the longest and, in case of ties, the lexicographically smallest. While sorting adds a pre-processing step, it streamlines the logic for selecting the result, making the solution more elegant. The time complexity becomes m*log m plus n*m, where m is the size of the dictionary and n is the length of s. The space complexity is m, due to the sorting step. This combined sorting and two-pointer approach strikes a good balance between efficiency and simplicity. Sorting the dictionary introduces a slight overhead, but this is offset by the clarity and efficiency it provides in selecting the result. By pre-sorting the dictionary, we eliminate the need for additional logic to compare lengths or resolve ties during the two-pointer check, making the implementation cleaner and easier to understand. After exploring the alternatives, we chose the sorting-based two-pointer approach because it balances performance and simplicity. Sorting helps us prioritize longer words and handle ties automatically, while the two-pointer technique efficiently checks subsequences. This combination ensures that our solution scales well even for large inputs. The key insight here is that the problem boils down to efficiently verifying subsequences, and the two-pointer method is both intuitive and effective for this. Additionally, sorting the dictionary upfront streamlines the entire process, removing the need for manual comparisons during the iteration. Together, these techniques form a robust and elegant solution to the problem, outperforming the brute force approach and simplifying the logic compared to an unsorted two-pointer method. While sorting the dictionary does add some overhead, the trade-off is minimal when compared to the benefits it provides. The process of sorting not only makes the solution more structured but also ensures that we can select the result with minimal additional logic. This slight increase in space usage is a small price to pay for the clarity and efficiency gained. Overall, the sorting-based two-pointer approach emerges as the most efficient and clean solution to the problem. It balances readability, performance, and scalability, making it well-suited for handling large inputs. By leveraging the two-pointer technique to efficiently check subsequences and incorporating sorting to streamline result selection, we achieve a solution that is both elegant and practical. This approach highlights the importance of combining simple techniques in a strategic way to solve complex problems effectively. In this problem, our goal is to determine the longest subsequence of a string s that exists in a given dictionary of valid words. A subsequence is created by deleting some or none of the characters in the string while preserving the relative order of the remaining characters. To solve this, we start by generating all possible subsequences of the string s. This can be done using a recursive function or backtracking. At each character, we have two choices, either included in the current subsequence or exclude it, leading to a total of 2 to the power of n subsequences for a string of length n. Once we've generated all subsequences, we stop recursion when we reach the end of the string. These subsequences can be stored in a list or set. Next, we validate these subsequences against the dictionary. By storing the dictionary in a set, we can perform O1 lookups for each subsequence. As we validate, we track the longest valid subsequence found in the dictionary. If there are ties in length, we can return any one of them or apply a lexicographical order preference if specified. Now, to make this process more efficient, we can introduce an optional optimization step. By presorting the dictionary by word length in descending order, we can prioritize checking longer subsequences first. This allows us to stop early as soon as we find a valid subsequence, assuming there are no ties in length. A few key insights are worth noting here. First, subsequences preserve the relative order of characters in the original string, so we don't need to consider permutations. Second, while generating all 2 to the power of n subsequences guarantees correctness, it is computationally expensive and inefficient for large strings. By sorting the dictionary and focusing on longer words first, we can reduce redundant checks for shorter subsequences. Alternatively, we can take a completely different approach. Instead of generating subsequences, iterate through the dictionary directly and check if each word is a subsequence of S. This can be achieved efficiently using a 2-pointer technique, which dramatically reduces the computational complexity. To implement these ideas effectively, we rely on specific data structures. First, we use a set to store the dictionary, enabling fast O1 lookups during validation. Second, we can use a list to store the generated subsequences, though for memory efficiency, we might choose to validate them directly without storing. Lastly, to check if a word is a subsequence of S, we use a 2-pointer approach. One pointer iterates through the string S, and the other pointer moves through the word being validated. If the 2 pointers successfully traverse the entire word, it is a valid subsequence. Now, let's consider the complexity analysis. Generating all subsequences has a time complexity of O2 to the power of n, and validating each subsequence against the dictionary takes O1 per word if the dictionary is stored as a set. The overall brute force approach is exponential and becomes impractical for large inputs. For this reason, the alternative 2-pointer method provides a much more scalable solution. Finally, it's important to handle edge cases carefully. For instance, if the string S is empty, there are no valid subsequences, so we return an empty string. Similarly, if the dictionary itself is empty, there are no words to match, and we again return an empty string. If no subsequences of S match any word in the dictionary, we return an empty string as well. Additionally, if multiple valid subsequences of the same length exist, we must ensure the tie-breaking rule is applied if specified, such as returning the lexicographically smallest word. Now let's revisit the optimized approach that avoids generating all subsequences. Instead, we iterate through the words in the dictionary and use a 2-pointer technique to check if each word is a subsequence of S. As we traverse the string S, the pointer for the word advances whenever there's a character match. If the pointer for the word reaches the end, the word is a valid subsequence. This method significantly reduces complexity because we only iterate through the dictionary and validate words in linear time relative to the length of S. The problem involves finding the longest word in a dictionary that can be formed by deleting characters from a given string S without changing the order of the remaining characters. The solution begins by defining an internal helper function is _subsequence, which checks if a given word can be formed as a subsequence of S. This function uses an iterator over S and ensures that all characters in the word appear in the same order in the string. To prioritize the longest words, we sort the dictionary in descending order of word length and then lexicographically for words of the same length. This ensures that the first valid word we encounter in the sorted dictionary is the desired result. The sorting is achieved using the sort function with a custom key, len x, where len x ensures descending order of length, and x ensures lexicographical order. After sorting, we iterate over the words in the dictionary. For each word, we check if it is a subsequence of S using the is_subsequence function. If a word satisfies this condition, it is returned immediately as the result. If no word in the dictionary can be formed as a subsequence, the function returns an empty string. This solution is efficient, leveraging sorting and early stopping to minimize unnecessary computations. Here, we start by importing the necessary packages and defining our solution class. The key method, findLongestWord, takes 2 parameters, the string S, which represents the input string, and dictionary, a list of words. The task is to find the longest word from the dictionary that can be formed by deleting some characters of S without rearranging the remaining characters. To achieve this, the dictionary is first sorted. The sorting criteria prioritizes words by length in descending order, meaning longer words come first. If two words have the same length, they are sorted lexicographically, ensuring that we consider words in alphabetical order when their lengths are identical. Once sorted, we loop through each word in the dictionary. For each word, we check if it is a subsequence of S by calling the helper method isSubsequence. If it is, we return that word immediately since the sorting guarantees it is the best possible choice. If no word matches, we return an empty string as the default case. The helper method isSubsequence determines if a given word is a subsequence of the string S. It uses two pointers, I and j, to traverse the characters in word and S, respectively. The while loop continues as long as both pointers are within bounds. At each step, we compare the current character of word with the current character of S. If they match, the pointer I4 word is advanced to check the next character in word. Regardless of whether there's a match, the pointer J4S is always increment to continue scanning through S. After the loop, we check if I has reached the end of word. If it has, it means all characters in word were found in order within S, so we return true. Otherwise, we return false, indicating that word is not a subsequence of S. The problem asks us to find the longest word in a dictionary that can be formed as a subsequence of the given string S. If there's a tie in length, we choose the lexicographically smallest word. For example, with S equals app plea in the dictionary, ale, apple, monkey, plea, we start by defining a helper function called is_subsequence. This function checks if a word X can be formed by sequentially matching its characters in S. It uses an iterator over S to efficiently verify this, ensuring each character of X appears in order. Next, the dictionary is sorted using a custom key. This key prioritizes words by their length in descending order, and if lengths are the same, words are sorted alphabetically. For this example, the sorted dictionary becomes apple, plea, ale, monkey. Now we traverse the sorted dictionary. The first word is apple. The is_subsequence function confirms that the sequence A-P-P-L-E exists in S, so it returns true. Since apple satisfies the conditions, it becomes our result for this input. For the input S equals app plea in the dictionary, A, B, C, the process begins with sorting. Here, all words have the same length, so the dictionary remains in lexicographical order as A, B, C. As we traverse the dictionary, the first word is A. The is_subsequence function checks if it can be found in S. Since it exists in S, the function returns true. As a result, A is selected as the valid word and returned. There's no need to check the remaining words because we've already found the first valid option based on the sorted order. The final output for this example is A. For the input S equals app plea in the dictionary, X, Y, Z, we start by sorting the dictionary. Since all the words have equal length, the sorted order remains X, Y, Z. We then traverse the dictionary, beginning with the first word, X. The is_subsequence function iterates through S but fails to find the character X, so it returns false. The next word is Y, and similarly, the function does not find Y in S, returning false. Finally, for the word Z, the function again fails to find it, returning false. Since no valid subsequences are found in the dictionary, the output is an empty string. This example highlights the importance of sorting the dictionary to efficiently check for valid subsequences while respecting both length and lexicographical constraints. The is_subsequence function, paired with sorting, ensures the solution is efficient with a time complexity of O, n*L, for subsequence checks and O, n log n, for sorting, making it well suited for typical input sizes. Time complexity for this problem can be broken down into two main components: sorting the dictionary and checking subsequences. First, we sort the dictionary using the sort function, which organizes the words based on two criteria, their negative length and lexicographical order. If we let D represent the number of words in the dictionary and average_len represent the average length of the words, the sorting operation takes O, D** log, D, time. This is because timsort, the algorithm used in Python sorting, operates with a time complexity of O, n asterisk log n, where n is the number of elements being sorted. The key function used during sorting, which determines the order based on length and lexicographical comparison, adds negligible overhead compared to the sorting itself. Next, for each word in the dictionary, we use the is_subsequence function to verify if it's a subsequence of the input string s. This check involves iterating through the string s using an iterator and comparing it against the characters of the word. If n represents the length of s, the inner loop runs proportional to n for each word. When applied to all words in the dictionary, the subsequence checks collectively require O, d*n, time in the worst case. These two components together give us the foundation for understanding the overall time complexity. When we combine the two components, the total time complexity is the sum of the sorting and the subsequence checks. Sorting contributes O, d*log, d, and subsequence checks add O, d*n, so the combined complexity is O, d*log, d, plus d*n. In practical scenarios, the subsequence check dominates because the product of d and n typically outweighs the logarithmic cost of sorting. Let's also consider the best, average, and worst cases. In the best case, the very first word in the sorted dictionary turns out to be a subsequence of s. Here, the time complexity simplifies to O, d*log, d, plus n, where n arises from the subsequence check on the first word alone. In the worst case, every word in the dictionary has to be checked, leading to O, d*log, d, plus d*n. On average, the time complexity tends to lean closer to the worst case, as most dictionaries require multiple subsequence checks before finding a match. This breakdown emphasizes the dominance of the subsequence operation in the overall computation. Now, let's look at space complexity. The sorting operation relies on Python's timsort, which uses temporary auxiliary memory proportional to the size of the input. Thus, sorting the dictionary requires O, d, space. For subsequence checks, the is_subsequence function operates with constant space because it uses an iterator to traverse the input string s without storing intermediate results. Iterators in Python are efficient and only require O, space. Since no additional space is allocated during the subsequence check, the overall space complexity is determined by the sorting step, which is O, d. When we combine these components, the total space complexity is O, d, making this algorithm quite memory efficient. To better understand the benefits of this solution, let's compare it to a naive or brute force approach. A brute force method would involve generating all possible subsequences of s, which amounts to 2 to the power of n subsequences for a string of length n. After generating these subsequences, we would check each word in the dictionary to find a match. This approach results in an exponential time complexity of O, 2 to the power of n asterisk d, because of the sheer number of subsequences. Additionally, it would require O, 2 to the power of n, space to store these subsequences. In contrast, the optimized solution avoids this inefficiency by directly checking each word in the dictionary against s using the is_subsequence function. This approach reduces the time complexity to O, d*log, d, plus d*n, and the space complexity to O, d. Clearly, the optimized solution is significantly faster and more space efficient, especially for larger inputs where the brute force method becomes computationally infeasible. Finally, let's solidify our understanding of the time complexity with a mathematical proof. Sorting the dictionary, which has d words, takes O, d*log, d. Checking whether each word is a subsequence of s involves iterating through s for each word, which results in O, d*n. Adding these two components together gives a total time complexity of O, d*log, d, plus d*n. For large values of n, the term O, d*n, dominates because n grows significantly faster than the logarithmic factor in O, d*log, d. Therefore, the overall time complexity simplifies to O, d*n in practice. This proof confirms that the optimized solution is efficient and scales well with the size of the input. When working on this problem, there are a few common mistakes to watch out for. First, always ensure you're handling edge cases, such as when the input string s or the dictionary is empty. Failing to validate these cases can lead to runtime errors that are easily avoidable. Next, avoid inefficiently generating all possible subsequences from the string s. This approach can be computationally expensive, especially for longer strings. Instead, smarter techniques like using two pointers can prune invalid options early, saving valuable processing time. Another pitfall is misunderstanding the dictionary structure. Don't assume it's already sorted unless explicitly stated in the problem. If sorting is required, make sure to handle it correctly, whether by length or lexicographical order. Additionally, pay close attention to tie-breaking logic. For example, if there are multiple valid subsequences of the same length, you're often required to return the lexicographically smallest one. Ignoring this requirement can lead to incorrect results. Finally, be cautious about character frequency mismatches. Just because a character exists in S doesn't mean it will necessarily form a valid subsequence with a word from the dictionary. Properly validate subsequences to ensure accuracy in your solution. Now, let's dive into some interview insights that are particularly relevant for this problem. Recognizing patterns is key here. At its core, this problem involves checking whether one string is a subsequence of another. Mastering the two-pointer technique is essential, as it allows you to perform these checks efficiently in O, n plus m, time, where n is the length of the string S and m is the length of the target word. Optimization is another important aspect. Sorting the dictionary by length in descending order and then by lexicographical order can help prioritize longer, valid subsequences, minimizing redundant checks. Modular thinking is also valuable. Break this problem into smaller tasks, such as validating subsequences, sorting the dictionary, and efficiently searching for the longest valid match. Finally, be ready to discuss trade-offs. For instance, brute force approaches have exponential time complexity and are impractical for larger inputs, whereas optimized methods like the two-pointer technique scale much better. Being able to articulate why these optimizations are necessary demonstrates a strong understanding of the problem. This problem also connects to several related problems that can help deepen your understanding. For example, LeetCode 392, which is the is-subsequence problem, focuses on the fundamental process of validating subsequences and is a great starting point. LeetCode 524, which is the exact problem we're discussing, challenges you to apply those concepts while accounting for additional constraints like sorting and tie-breaking. LeetCode 300, the longest increasing subsequence, builds intuition for dynamic programming and subsequences in a broader sense. Similarly, LeetCode 1143, the longest common subsequence, compares two sequences comprehensively and introduces a more advanced approach to solving these types of problems. Now, when it comes to alternative approaches, brute force is often the simplest to implement. By generating all subsequences of S and checking them against the dictionary, you can solve the problem, but at the cost of O, 2 to the power of n, time complexity, which is highly inefficient for larger inputs. On the other hand, the two-pointer technique is far more practical. By iterating through S while checking if each word in the dictionary is a subsequence, you can achieve a time complexity of O, n asterisk m, making it significantly faster. However, pre-processing the dictionary, such as sorting it, is often necessary to get the most out of this approach. Another alternative worth considering is the bucket dictionary approach. Here, you pre-process the dictionary by grouping words based on their starting characters. As you traverse the string S, you can incrementally match and filter out words from the relevant buckets. This allows for faster lookups during the traversal phase, which can save time when working with larger dictionaries. The trade-off is that this method requires additional pre-processing time and memory to set up the buckets. While it's not always the first choice, it can be a powerful optimization in scenarios where the dictionary is large and the input string is long. By combining these techniques and weighing their trade-offs, you can tailor your solution to fit both the problem's constraints and its real-world applications. Great job! To wrap up, we reviewed the key insights and techniques for solving this problem efficiently, such as using the two-pointer approach. Remember to practice similar problems to strengthen your skills. Thanks for watching, and I hope to see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!